Hello friends, welcome back. Today we will be learning about permutations and combinations. Okay, so let's first learn about the fundamental principle of counting. There are two different rules here, both completely different. Fundamental principle of counting, right? Okay. The first one is called the rule of product. Which states that if one experiment can be done with m different outcomes and another experiment can be done with n different outcomes, then both of these experiments can be done with the total possible of m into n outcomes, right? So m multiplied by n, that is the total number of possible outcomes in which both these experiments can be performed. So let us learn this with an example. Let us say you stay at city A, right, and you want to go to city B, and there are three different modes of transport or three different routes to B. Say you take the first one or the second one or the third one, right, and you reach city B. Now from there you want to go to another city C, and now you have four more modes of transport here, right? So how many total different ways are there for you to go from A to C? Let us see. The first one, from A to B, you can go in three different ways. The next is four. Now, if you take, say, this one, right? After this, you can go to C in again four different ways. Similarly, for the remaining two. So we see that 12 is the total possible number of ways. This is what the rule of product says. If there are m possible outcomes for the first experiment and n for the second experiment, and both of them are performed, then the total number of m into n ways. Okay. The second is rule of sum. The rule of sum says if one experiment can be done in m different ways and the second can be done in n different ways, then either one of them can be done in m plus n ways. Okay, there it was m into n, here it is m plus n. Okay. Now again let's learn this with an example. Say you are in the same city A. Now you want to go to city D now, and you can go to city D in three different ways, right? And suppose you want to go to city C now. City C you can go in four different ways, right? So suppose you want to go to either of these cities, how many ways can you go? Well, you can go, since nothing has been mentioned about the connection between C and D, we will assume that you cannot go from C to D or vice versa. So we see that the total number of 7 different ways for you to go to either of the cities, right? You can take any of the 3 routes to D or any of the 4 routes to C. Total number of 7 ways. That is what it says. If there are m outcomes for the first, n for the second, then total is m plus n. Right? These many number of ways exist for either of the experiments to be done. So we can actually generalize both these results, and that is how these find a lot of use in permutations and combinations. These complete the fundamental principle of counting. Let us now look at what a permutation means. Permutation is nothing but an arrangement of objects. So suppose you have n different objects and you want to choose m of them and then arrange them in different ways. So the total number of ways is what permutation actually means. So there are different ways of doing this, and for our we will take a few things constant here. We will always be taking n different objects for the purpose of understanding the different cases, and we will be choosing r objects every time. Okay. The first is without repetition. Right. So this is my list of say slots where I want to place those objects once I have chosen them, right? And I have r different slots, so I can choose a maximum of r objects, right? Whereas I have a total of n. It goes without saying that n must be greater than r, otherwise greater than or equal to r. Otherwise, this doesn't make sense, right? So now you see, for the first one, out of my n objects, I can take any. I can put any of those n objects. Now, once I have put that, my the arrangement I am doing is without repetition, right? So I am not getting the. Say I have put an apple in one. I am not getting another apple to put in two or in any of the other objects. Now I can do it only in n minus 1 ways. Similarly, n minus 2 for the next, right? So we get a result for this, and that is actually NPR, which is n factorial by n minus r factorial. Okay. So this is the total number of ways I can permute n objects taking r at a time, or I can arrange n objects taking r at a time. Okay. Now, factorial. I assume that you all know what a factorial means. N factorial here means the product of all natural numbers from 1 till n. So 5 factorial means 1 into 2 into 3 into 4 into 5. Right. And we take 0 factorial as 1. That is basic assumption we take here. Now, the second is with repetition. Right. Now, instead of let us draw the same box again. So we have again r slots here, and we have n objects. But now, once I have say put an apple in the first one, I have another apple left, and I can put that again, right? So instead of n minus 1, I again have n choices for the second. Similarly, for the third box, I again have n choices, right? This goes in right till the rth slot. Hence, the total number of permutations here is not NPR, it's directly n power r, right? So suppose I have 10 objects and I have only 2 slots. So in the first one, I can put I can fill the first slot in 10 different ways. I can fill the second slot in also 10 different ways. So I'll have nothing but 10 power 2, that is 100. Whereas in the first case, it would have been 10 into 9. Because once I have exhausted my first thing, now I have only 9 other objects remain, 9 other objects for the second slot. So it would have been 90. So here we see there are 10 more possibilities in the second case. The third is actually third is nothing but in a way a superposition of these two. You now have of every different kind of an object you have say multiple number. Okay, so again we have n objects, out of which p are of one kind. Say the first kind. We will assume that there are only 3 kinds of objects right now. There are q of the second, and r of third. Okay. So how many different ways can you permute this? Well, I'll give the result first. The result is n factorial by p factorial into q factorial into r factorial. How do we get that? Pretty simple. There are n ways. Now you can, let us say you have chosen all of them and you are now permuting them. Now here we assume that we're actually permuting, we're taking all of them. It's not that we're choosing r, we're choosing n itself. Right? In the previous 2 cases, we're choosing r. Here we are not choosing r, we're choosing all n of them. Right? Now that can be done in n factorial ways. But we see that the first kind will be occupying p different slots. And actually, if you permute any of them, it doesn't matter because all of them are identical, right? An apple in the first and an apple in the fifth will not be different than an apple in the first and the fifth one will transfer to the first and the first to the fifth, right? It will still be the same. So similar, that is the reason why p factorial comes in the denominator. So we need to divide it by p factorial ways. Similarly, q factorial for the second and r factorial for the third. This is how we get the number of permutations of n objects taken all at a time, which has which has P of the first kind, Q of the second, R of the third, and so on. Okay. The fourth is a very important one called the circular permutations. Now in circular, here actually we were considering linear permutations, right? I was arranging them in a straight line. Well, in a circular, say you're sitting on a table, right? Suppose it's a dinner table, and you have invited a few guests. Now what you do is, suppose you have to find out, suppose there are, say, 6 different chairs. Okay. Now how can you arrange your guests on these chairs? So that is what circular permutation is concerned about. So now had this been a straight line, you have 6 objects, right? 6 guests and 6 different chairs, and you can sit them in 6 factorial ways, right? You can take the first chair can be occupied with 6 persons, any of the 6 persons, the second in 5, then 4, 3, 2, 1, so it's 6 factorial. But here, note that those 6 factorial, suppose my first one is like this, 1, 2, 3, 4, 5 and 6, right? Suppose this is how I sit there. Now second is, suppose start with 2, then 3, 4, 5, 6 and 1. Well, actually since it's a round, it's a table, right? Circular table. It doesn't matter, right? Because if I look at it from this side, it still is 1, 2, 3, 4, 5 and 6. Right? So, this will actually, similarly if I write 1 here, in the next one and 2 here and 3 here, again it will give me the same thing. Right? So, circular, that is why it decreases the whole thing by n. And hence, here instead of n factorial, you will have n minus 1 factorial. Right? Now there is another case in this. Now this is, if I consider the two separate clockwise and anti-clockwise rotations to be different, right? So suppose they are same. So for circular, we have n minus 1 factorial, right? But if we consider both clockwise as well as anti-clockwise to be the same, then we have only in that case, we will have only n minus 1 factorial by 2, right? Because there are equal number of circular permutations as well as the anti-clockwise, because there is no distinction between them. The only thing is, if we distinguish them, we will have n minus 1 factorial. If we don't, we will have half of that. Okay. So that is permutations for now. We will be looking at them. We will be taking them up in the question session. The next slide, next video. And let's now look at what combinations are. Okay. So what I was doing in permutations was, out of my n objects, I was choosing R and then I was arranging them in different ways. Well, if I don't arrange them, I just select those R objects, that makes it a combination. Right? So, combination is nothing but selection of objects. So, permutation in another way is the next step to a combination. You, out of your n objects, you choose R objects in different ways and then you permute them, right? Now, the first is again without repetition. Okay, in without repetition, this is the result NCR. So for combination we write C, whereas for permutation we write P. Okay, and this is equal to n factorial by n minus r factorial Right. So it's actually pretty simple from this. Look at it this way. Okay, we can choose R objects from a total of n objects in NCR ways, which is nothing but n factorial by n minus r whole factorial into r factorial. Now once you have chosen them, if you want to arrange these R objects, how many ways can you arrange them? Well, we can arrange each of them in r factorial ways, right? So when we multiply this with r factorial, what we get is n factorial by n minus r whole factorial, which is nothing but npr, right? So we see that from each combination we get permutations. Okay. So without repetition, you get ncr ways. With repetition. Now again, the same thing. Instead of our now once I say out of my n objects, I am supposed to choose r, and I have already taken the first, say an apple for the in the first case. Now I have more apple left. Okay, let's say there is an infinite number of apples. You can replace them again and again. So I have another apple left, which I can choose again. So because of this, the number of possible selections actually increases, right? And the number is given by n plus 1 minus r cr. Oh, sorry. This is n plus r minus 1 cr. So if you write this is nothing but n plus r minus 1 factorial by r factorial into n minus 1 factorial. Okay. So instead of ncr base, we have n plus r minus 1 cr. Now there are a few more cases. Suppose out of your n objects, you want to choose r, but out of those r objects, you are sure that k objects will always be included. Okay. So now this is what makes it restricted selection or permutation. So suppose you are the manager of a football team, and say you have a squad of 16 players and you have to choose 11, right? So your n is 16. Your R is 11, but you're sure that your striker, one of your strikers, a goalkeeper, and say a midfield player, both of these three will always be included, right? So this is what this selection or restrictive selection or permutation means. So instead of now out of 16 players from which you have to choose 11, 3 are already always chosen, right? So that is one case. It is called always included. So let's say we have k objects which will always be included. Now in that case, the total number of selection is n minus k c r minus k, right? So say 16, 11 and 3 in our case, for our example. Now out of that we see that 3 are always included. So out of now the total number of selections left for us are nothing but there are only 13 players remaining, out of which we can give a total number of 8 slots, right? Or 8 different positions. So out of 13 we can choose only 8, or 16 minus 3, that is 13, and 11 minus 3, which is 8. So we see that this is the number of permutations selections left. Now obviously to find out the permutations for this case, it's nothing but this many, this is the total number of selections, but this will not be multiplied with r minus k factorial. There are 11 positions left, right? Or there are 11 slots. So this should still be multiplied with r factorial. Please be careful, it will not be r minus k factorial, which is the multiplication factor here. Instead of those 8 players which are chosen afterwards, you can still permute the 11 in all different ways. So you have r factorial. Okay. So this is the total number of selections, whereas this is the total number of permutations. Okay. There is obviously the second case, which is just opposite. Instead of always included, we have never included. Right. So say in your squad of 16 players, you have two who are always who are badly injured and now they just cannot play the tournament, right? So instead of 16, you just have a total of 14 players left for 11 positions, right? So instead of n, you have n minus k left, whereas you still have those r positions, right? So you have n minus k cr. This is the total number of selections now. Okay. Whereas now these R players can be permuted in R different R factorial ways, and hence that will give us the total number of permutations. Right. So we see that in a restricted selection, you have to in these specifications you have to cleverly include or exclude some players, and that gives you the total number of selections or permutations. Okay. Now a few properties of the combination of the combinations C. First and the most important is NCR is equal to NC n minus R. Okay, let us first understand this. Understand it. Now, why can we write NCR equal to NC n minus R? Well, you can very easily prove it algebraically, but let us understand why the essence of this. Okay, so what does NCR mean? Now, well, NCR means out of your n objects, you are choosing R. Right? Let us for now assume that all of them are different, all of them are unique, and you're choosing R which is not equal to n. Okay. Now, if you are choosing R, it's the same thing as the number of ways you are actually excluding excluding n minus R. Right? So you are either choosing R or rejecting n minus R. So the answer should be same, right? You are the number of cases of choosing R objects from n or the number of cases of rejecting n minus R objects from n must be same. Hence, NCR must be equal to NC n minus R, right? Otherwise, you can actually prove it algebraically also and see for yourself that suppose, say out of 10 players, say I choose 5 for a basketball team, right? Now, suppose I choose this 5, that means I am actually rejecting the other 5, right? So actually you see that they will always turn out to be the same number. They have to, right? You choose one, you actually reject the other bunch of players. The next is a very useful property. NCR plus NCR minus 1 gives you n plus 1 CR. Okay. Again, you have to bit clever while doing this proof, and you can show that this actually holds true. Now NCR, well, if you look for NPR is n factorial by n minus r whole factorial, right? So NPR is actually well, let us look at it from the beginning. Let's say r varies from 0 to n. R can be 0, right? So NP0 here will be nothing but n factorial by n factorial, which is 1, right? But then suppose you increase it further and further, NP1, that is n factorial by n minus 1 factorial, which is n. The next is n factorial by n minus 2 factorial, which is even more, right? So, and let us look at the last one, n factorial by 0 factorial, which is n factorial, right? So, you see that NPR actually increases when you increase r from 0 to n. Whereas for NCR, NC0, that is n factorial by 0 factorial into n factorial, which is 1, and NCN is also the same thing, right? From this rule, from the first rule, you'll always get the symmetric parts to be the same. Hence, you can see that NCR will be greatest. Now there are two different cases here, and it is pretty obvious why. Now, if R is odd, okay, so if R is odd, you'll have say, let's say R is 5, right, and you have say 8. When N is odd, R can actually take all the values, so we have to consider N. Suppose N is say 5, right? So now let us vary R from 0 to 5. So we see phi C0 and phi C5 are same, phi C1 and phi C4 are same, phi C2 and phi C3 are same, right? And they are actually increasing. They are increasing from both sides. But now we see that there is no other, nothing else remains, right? So we see that will be greatest when R is equal to N minus 1 by 2 or N plus 1 by 2. For both of them it will be equal and the greatest. This is when N is odd. And similarly, for the next one, R is equal to N by 2 when N is even, right? Suppose I take N equal to 6. So I have 60, 66 are same, 61, 65 are same, 62 and 64 are same, 63, which is still greater than 62 and 64, will be alone greatest, right? So this is another property. And then we have this one, NC0, NC1, NC2, NC3, all the way till NCN is actually 2 power n. Okay, so we see that actually, let's say 60 plus 61 plus 62 like this till 66 will always give us 2 power 6. Okay, so that concludes all the properties and theorems. Well, we cannot always include all the properties here. The questions will always have something new. So we will have the question session in the next video, in which we will be covering as many different ways, different kinds of questions. And so thank you so much. Stay tuned.